Hello everyone, welcome to this video. In today's video, I'm going to show you how to do an FEA based validation of a nano-indentation test. In this case, I have got a model from a subscriber and the subscriber asked me to show how that model can be used to calibrate with the experimental data so that the FEA model has been validated and it gives you a nice result. So the model file had two models, a 3D model and a 2D model. So I have shown the whole procedure with the 2D model, which is an axisymmetric model. And you can see the experimental data and also the model data shows very good relationship, which can be further improved by using the procedure, which I have explained in this tutorial. So I hope you will enjoy it and you will learn about nano-indentation test and its validation through finite element analysis in this video. So see you on the other side. Okay, let's look at the files which are being sent by the subscriber and see what's in the model file. Okay, so we are being sent these two files, but this is a CAE file. This is a journal file for that CAE. Then there is some data on the Excel sheet, and I think it's an experimental data for the alloy. And if you look at this, so this should be the indentation and the load. So let me plot this. So I'll go insert graph, maybe a line. So this is how it looks like. Maybe make it to the separate chart or something so it's better visible. So here you see, and the force, if you go back to the sheet, then force is in micronewtons and this depth is in nanometers. So we will be working with the similar sort of dimensions to compare the results directly in Abacus. So this force is in micronewtons and this is in nanometers. Okay, so this is the data where you put the indenter in and then you take it back, retrack it, and this is how the force really varies with depth of indentation. Okay, so this is the input file and this is the CAE file. So let's go start with the CAE file. So I'm just opening it in Abacus CAE. I hope it's the CAE file was created in a compatible version. If you are using an older version than the file version which was used to create this file, then it might not open in your CAE. So this is one of the things which we always have to look for. Okay, CAE is on the screen. So you see there are two models here, or other three. So I don't know what is this, but I think this is an empty model. There are no parts, nothing there. So I may delete this to keep our life more simple. And now we are end up with two models. One is this model, and it seems to be 3D model, which is the material, and it seems to be maybe quarter or more than quarter, 1/3 of the model. Okay, we go and now we look at the second model. So I will close this and I will look at the second model. In the second model, again, there are two parts. So I will select the second model. Okay, so this is a 2D model. Let's go to the part. So you have an indenter as this, then you have a substrate as this, and this is pretty fine. Again, you don't need this kind of fine mesh here. You can use some kind of bias here that could improve the convergence, but that's fine for now. This is a big model in my opinion. QD, the mesh, and you see these are around 18,843 elements. Okay, the second part is the indenter, and again this is fine most probably. So next thing is the properties. So again we have three properties here. Aluminium is density is given because we need to work with explicit dynamic in this case. Again, this is user's preference. Elasticity properties are given. Hopefully the units are consistent, and then the plastic part of the spin curve is given as well. Next is the diamond, most probably the elastic density and the elastic part, which is the same as the 3D model. Then if you look at SI, that is also same as the previous curve. Again, in this case, I think the user is assuming ideally plastic material. So this is fine. Let's see which material is what. So if I go here, there are two materials used. One is diamond, which is for indenter, and the second one has used, second section is user properties of aluminium. And again, that must be for the second case. So let's look at this. And you can see the section assigned to this part is aluminium, with aluminium properties as homogeneous material. And if you select the diamond, then in this case, it's a diamond properties which are being used. So this looks okay. This is assembly, so they have assembled everything, and this looks fine as well. Okay. Step. There is a dynamic explicit step with a total time of 0.1. Rest seems to be all default. Okay, there is some mass scaling used, and I think that's just their preference for the time being, maybe to improve the time increment size. Then if you look at the interaction, so we have one interaction in step 1, and that is a surface to surface contact with integration and with interaction properties of 1. So now let's look at the interaction properties 1, and these are frictionless properties and hard contact being used here. So these are fine. This is a less complex model than the 3D one, I think. Then this top surface of the indenter is coupled with the reference point with all the degrees of freedom, which is U1, U2, and UR3, which is the rotation. Anything else? So we have a coupling constraint, which I already showed you. And I don't think there is anything else which should be here. Now we go to the loads, and in the loads, we don't have any loads here. But we again have some displacement boundary conditions. So this is U1, which is 0 for this case. U1 is the lateral direction, which is X direction, horizontal direction. Then this is U2, and again, this is being compressed to a depth of 0.5. And I think this is more consistent because it's going up to 0.35 or 0.37 or something, most probably. It's around 0.362 is a max. So 0.365 or something like that should be okay. So we can change this to 0.365 if everything is in micrometers. And we have to look at the amplitude as well, because that has to go down and then go up as well. So we will check that later. The rest should be the boundary conditions. So UR3 rotation is fixed, and this one is propagated. So I think these are all the boundary conditions for the bottom surface. This is X symmetric and this is Y symmetric. This is again X symmetric, and again, hopefully this one was this should be taken from the test condition. If initial conditions, I think nothing else is there, so we need to move to the next one. So this is the mesh, and now if you look at the mesh on individual parts, so I'll first select this part, and you see these are axisymmetric elements. Similarly, if I check the other one, and so this should also be axisymmetric model with this. So this looks fine. I mean, for the time being, I don't see any problems. Okay, the only thing left is the amplitude. So I go to the loads, tools, amplitude manager, and see how the amplitude is defined. So at 0, this is 0, and at 0.365, it should be 1, right? And then we know that from, no, not 0.365, but rather it should be the total time of the increment. So that is 0.1. So we can use 0.1 to be 1, and then 0.2 to be I think we need to go back up to a force of 0, which should be at around 292, which is 0.292. So if I go back, so this should be, so okay, so it should be 0.05, 0.5 or something. I think this is more correct. It will load and then it will unload. So again, this is approximated. You can compute based on your own current. Still, I need to see how long it's going to take to finish. So let me see how it works. So now I will start the job, create, and I will call it Nano Test 1 XC system, and I will always go with double precision and full precision for explicits. And now I will try to submit this job. So you see job has started with no error, so this means everything is defined correctly. So now we have to wait patiently and see how the simulation works. Again, we need a finer mesh on this surface because these two should be conforming. So as you can see, this job has been running around an hour now, and it has only reached to a total step time of 0.042, and it has to go up to 0.1 with the maximum depth, and then it's retreat back. So total time will be 0.2. So I think this is very slow in my opinion. So what I can do, so I'm going to kill this job now, and I'm going to go and delete the step, which is this one. But before that, maybe I should check what interactions are there. So there is one interaction between the two surfaces, and then there is a constraint which is between this surface and the reference point. And then in the loading, we have the forces, and then we have displacements and also x and y symmetric. So y symmetric, x symmetric, x symmetric, x symmetric, and then fixing this in lateral direction while moving it in down with a maximum displacement of 0.39365 or something, and then coming back, bring it back to 0.3. So let's do this. What I'm going to do is step, and I'm going to delete this step now. Delete. So this is fine now. Let's leave it like this, and then let's go back to the step. Now I will create a static general step, and I will run it for total time of this. I will use a large number of increments. Initially it should have 0.001, and finally I think it should go up to use this kind of value. Again, we will see how it goes, and then we will come back and change it. Interaction, so we need to see if this is already existing. So okay, this survived the step definition, but this will have gone. So in this case, we need to create a surface to surface contact, and I don't know which one is which. So this is indenter surface. That has to be the main surface. So that's this. And now I will select the secondary surface. For that, I will use straight surface with interaction properties 1, and use everything as default for this as well. So this is done now. So loading. For loading, these boundary conditions are there. So this was bisymmetric. I go back here. So this is the bottom. So this is there. X-symmetric is there. Y-symmetric is there. And then x-symmetric for this is there as well. So we only need to fix this in step number 1. I'll select. Okay, let's select from the reference point, which is this, I think. Yep. So, and I will fix this set to be 0, while U2 I give a value of 0.365, which is the max. And then for amplitude, I'm going to use the same as amplitude 1. Okay, and now I need to see what I have to do with the amplitude function, because that needs to be changed, because at 0 it will be 0, then at, let's say, 0.6 or something, it should be 1, which is open that. Then at 1.0 should be 0.584 times that displacement, and that will make it go back to around 0.3. So this way we will keep the balance of everything. Okay. The other way around could be we could give the actual values here and we keep that value as 1. So it's your choice. So hopefully this is fine. I'm ready with 1. And now we go to the mesh and we change the mesh type most probably. So I'll select all the elements and I will choose standard elements as this. And then I will do the same for the indenter. Done. Standard. Done. Hopefully this is fine now. So we go and now we will submit, create another job. And we call it nano test 1 XC standard. Okay. Always go with full precision. Then submit. I hope this will increase or at least doesn't give any issues, because generally static general has always end up with a lot of convergence issues. But we will see how it progresses. So I think all the definitions are correct. Now you see it's going pretty well. And time increment is also increasing. So it took over 1 hour to reach to this point for the explicit case, but in this case we have done well. Hope all the things are working fine, but we will check once we reach to the final one, which is 1. So things look promising, but let's check to be on the safe side if contact has been established. And yes, you can see the contact is working fine. So okay, the problem is we have given a positive value, so we need to give a negative value in there. So I'm going to kill this job now. Sorry about that. And then I go to the load, then I go to displacements, edit, and I'll give a negative value because we have to go in the negative direction, which is the downward direction. Apologies, it's almost night time now, so I'm a bit tired. 110, so yeah, it's gone. So submit again. So there are a certain number of outputs. Let's check again if everything looks sensible. And now you can see that it is going in the right direction and contact has been established as well. So let's wait and see, and how long it takes. Once it finishes or it crashes, I will come back and show you what could have gone wrong, or if the results are ready, then we will try to post process. So as you can see, the simulation is finished. Let's look at the results quickly. And now press this. So you see it has, if you display this, so it goes indents, and then after 0.6 it goes back and it creates this kind of indentation mark. Now to plot the force displacement curve, what I'm going to do, I'm going to go to the XY data manager, create field output, then I will say unique nodal. What I need is a displacement in vertical direction and reaction force in vertical direction, which is RF2. And then I want to plot it at this. So let me plot and see how it looks like. So you see, this is how it looks like, loading and unloading. So I will save them, this, and now I'll combine them, operate on XY data, combine, and I will use an absolute value of the displacement and then an absolute value of the reaction force, and save. So this is our first set of data. I will delete the rest of the stuff. I will delete this as well. If I plot now, so this looks something like this. So it loads, then it unloads. Now if I want to create, I'll save this file first in case it crashes. Now I'll create bring the experimental data here from the Excel sheet. So I'll go to the Excel and I'll copy the whole thing in Abacus here. And then here, this is the displacement. So I will select displacement, and this should be the force. Okay, if I plot this, then you see this will look like this, and I can call this as experimental data. So now if I plot this with this, then you will see this data is much higher than this, because this is only going up to 0.8. So maybe there is something wrong with the unit conversion, while the values on the x-axis are also different. So this means we need to convert them. So let me convert that, and then we adjust the plots. Okay, so now what I have done is basically I ran the simulation with first set of data, and it was giving a very low results. So as I told you before, I have to go back and start changing the material properties. So in this case, I'm not right now playing with elasticity. So what I've done is basically I have increased the hardening of the material, because if you remember in the actual data, if you plot this, so this was the initial data which was given in the material model, as I showed you before. So that was giving me a linear hardening. So a user might have used a linear hardening curve. So we don't need to define all these points if it's a linear hardening. But if it's a non-linear hardening, then you have to go with that. And if it's a non-linear hardening, then it gets more complicated, because in that case, it might be more useful to use some kind of analytical relationship like Johnson and Cook model, or deformation plasticity, which uses Ramberg-Osgood function, and change the parameters to change the whole curve rather than changing the individual value. So what I have done, I've used the first value since it's linear, and I have used the last value as my data, because the rest are all interpolated linearly, so I don't need to define all these. So this way, what I have done, this value was giving me a very low value, as I showed you a few moments ago. So I started increasing this until I get to a good fit with the stress force displacement curve. So so now you can see I've used a value of 0.5, 1.2. Initial yielding is still the same, but you might have to change this as well, depending on how good the fit is. So now if I go, you have to do it one by one. Every time you basically run the analysis, you go to visualization, and then you look at the results. If they look okay, then you create the XY data, as I did it for XY data 1. So this was the initial one, if you remember, and it was very low as compared to the actual data. And then I started increasing it incrementally to get some idea. And you see, then I reached to this point, then I increased it further, and then I was able to go up to this. And the last value, which was 1.2, I just showed you, give me a very good fit. So you see it's going very well. Still, there are some differences, so which can be adjusted by adjusting the initial yielding. So you can also go back to the property module here and change maybe this as well. So maybe if you increase it to 0.1, let's see what happens with 0.1 to give you an idea what is happening with the initial yielding. It's the initial yield strength of the material. So I will run it again. Each simulation in 2D is taking around 20 minutes for my PC, and 3D one, which I showed you at the start, was at I think after 4 hours even, it was not finished or reach up to 10% of the simulation. So 3Ds are more expensive. So again, you can decide what you want to do, and also standard is cheaper than explicit in these kind of problems. So I'm going to submit this now, and it's going to take 10 minutes, and then I will come back and show you how the results are by just changing the initial yielding of the material. Okay, so as you can see, the analysis is finished. So I will go to results. So these are the results which I already showed you as compared to the experiments, and we are most probably going to compare with the experimental data and the last one to see if by increasing the initial yielding has improved anything in the model. So I'm going to go and press create field output. I will select the reaction force 2 and the displacement in 2 direction, and I'm going to plot it for the reference point at the top of the indenter. So, and then I will say as is. And now I'm going to combine these two together. So operate on XY data, combine, and I'm going to use an absolute value of U1, which is an horizontal axis. And then the absolute value of the reaction force, which is this one. Press save. This is XY data 6. So now if I plot this, this looks something like this. Again, you can change the mesh and also play around with the other properties like friction, etc. to be smoothen it down. Also, the number of outputs will change this trend as well. So now if I compare this with this, then you can see there's only a slight difference by changing the initial yielding. There is a slight lift. If I now bring in this, then it looks like this. So you can see initial yielding has some influence, but it's very small. So either if you want to increase it, you need to increase it drastically to really see a big difference between them. Also, since your simulated response is less stiffer than this, so you might have to play around with the elastic properties if they are not fixed for this material. Again, this is an alloy, so I don't know the value. So maybe if I change it to 68 or something and rerun it to see what happens, then that will also give me an indication that elastic property changes the results or not. So let's run it as the last time, and then I will just end after showing you the results, since you should now know how to really fit a typical force deflection curve which you obtain from a nano-indentation test with the experimental data. So I'll be back once this is finished. Okay, so as you can see, the simulation is finished and without any problems. So I'm gonna go now and check what happened. So just to remember, what we changed in this case was elastic modulus. I go to visualization, I go to the job first, and then I say results. Now I will delete this. It's from the last step. If you look at the results, they look pretty much the same. It goes down and then goes up. The remaining plastic deformation is there. Create output 2dB field output. Again, the same thing is already selected, so I'm going to select only the reference point. Save as is. And now it is done. So now we go to create, operate on XY data, combine, absolute, this, comma, absolute, this, save. And now I will delete this one. And I will plot this to see if it looks okay. So I think this looks fine. And yep. So now what I do is I'm going to compare this with the last plot to see if there is any difference. You see there's a significant difference. The 7 one is the one which is the recent, and it has gone up slightly with the Young's modulus. It should be the case because we are increasing the stiffness. If I compare with the experimental value, then you see it's much closer to the experimental value, although it's going up from here. So from this side, you might have to decrease the yield strength to bring it down. So again, you can play around with all these factors and see which one can give you the best fit. And this is the way you basically fit the actual experimental data with the computational model. So if you have any question, comment below. Otherwise, looking forward with some more interesting videos in the near future. Thank you very much.